In the world of mathematics, there are some problems that aren't just hard, they're considered impossible. They literally define the boundaries of what we think we can know. Well, today we're diving into a story about one of those boundaries, a wall that has stood firm for 2 full centuries, and the incredible claim that someone has finally actually broken through it. So let's just kick things off with a huge question. What if an equation, one that generations of mathematicians just accepted as fundamentally unsolvable, actually wasn't? What would that even mean for what we think of as the limits of human knowledge? That's exactly the rabbit hole we're going down today. All right, to really get a handle on this supposed breakthrough, we first have to understand the problem itself, because at the very heart of this story is a type of equation that has stumped some of the greatest minds in algebra for hundreds of years. We are talking about polynomial equations. And yeah, you've probably seen these before, maybe gave you some headaches in a high school algebra class. They're just expressions with variables, x, raised to different powers. Solving them just means finding the values of x that make the whole thing true. We call those its roots. For the simple ones, it's pretty straightforward. But as they get more complex, oh boy, do things get tricky. The specific beast we're looking at today is the 9th degree polynomial. That number 9, it just means that the highest power of the variable x in the equation is 9. And let me tell you, in the world of algebra, that number has been a symbol of impossibility for a very, very long time. Yeah, for mathematicians, trying to solve this wasn't just another homework problem. It was like an unconquered mountain peak, one of the last frontiers. It really represented this hard limit on our ability to find perfect, exact answers using the tools we had. So, why? Why was it considered so impossible? And that brings us to the history. See, this isn't a new problem at all. It's a challenge with a giant 200-year-old wall built right in front of it, a wall that was constructed by a true mathematical giant. So let's take a quick trip back in time. Way back in the 16th century, mathematicians figured out general formulas for 3rd and 4th degree equations. Awesome! But then, progress just slammed into a brick wall. In 1824, this brilliant Norwegian mathematician, Niels Henrik Abel, proved something that was absolutely staggering. He proved that there is no general formula to solve equations of the 5th degree or higher using only the standard tools: addition, subtraction, multiplication, division, and taking roots. This became known as Abel's impossibility theorem. And this is so crucial to understand. Abel's theorem wasn't just a hunch, it was a formal proof. It built a mathematical wall. For over 200 years, it was just accepted as fact that any equation of the 5th degree or higher couldn't be solved with a nice, clean formula. The best you could hope for was to get close with approximations, but you could never find the exact perfect answer. But what happens when someone just walks right up to a 200-year-old wall and claims they found a secret door right through it? This is where our story takes a really dramatic turn. Answer Professor Mourad Sultan Ezouidi. He's an internationally recognized mathematician who has poured decades of his life into this exact problem. And he's claiming to have done what everyone thought was impossible by developing a totally new method, Ezouidi's theorem. I mean, this quote from Professor Ezouidi's work really says it all, doesn't it? He's not saying Abel was wrong, not at all. He's basically saying that Abel's proof was only true for the mathematical tools they had back then. Ezouidi's claiming that by inventing a completely new set of tools, that old limit, it just doesn't apply anymore. Okay, so how in the world does this new method supposedly work? To get what a huge deal this is, let's just put the classical approach side by side with his new one. The difference here is like night and day. On the left, you've got the classical methods. They hit that hard wall at the 4th degree, and from then on, it was all about approximations. The philosophy was basically one of acceptance. Some things are just unsolvable. But Ezouidi's theorem, over on the right, claims to get exact 100% verifiable solutions. And the philosophy? It's the complete opposite. It's a rejection of what he calls mathematical fatalism. It's the idea that every single equation has an exact solution just waiting for us to find it. So conceptually, here's how it works. Imagine the equation isn't just a flat line of symbols, but more like a complex, folded-up piece of origami. First, the theorem carefully unfolds it, reorganizing it into these nested layers. Then, it uses the hidden symmetries within those layers, kind of like finding a secret pattern in a crystal, to transform it. And finally, once it's in this new, perfectly organized shape, the exact answers, the roots, can just be read off. No guesswork, no approximation. Now, if this claim holds up to the intense scrutiny of the wider mathematical community, and that's a big if, the implications are just profound. This isn't just about solving one really hard problem. This line from the source material really gets to the core of it. This potential breakthrough isn't just a new answer. It's a completely new way of thinking about what kinds of answers are even possible. It challenges the very definition of solvability that we've been working with for 200 years. So let's just boil this down. What are the big takeaways here? First, a massive mathematical barrier that has stood for 2 centuries might actually be broken. Second, it suggests that maybe when we call something impossible, it's just a limitation of our tools, not a fundamental truth of the universe. Third, the core claim here is that every single polynomial has a perfect exact solution out there. And finally, if this is true, it could trigger a revolution in science and engineering, everything from physics and signal processing to cryptography, pushing entire fields away from good enough approximations and toward absolute algebraic perfection. And that leaves us with one last, really provocative thought. Professor Ezouidi's work, whether it becomes the new standard or not, forces us to ask a really powerful question. It's a reminder that sometimes the biggest breakthroughs don't come from finding a new answer, but from finding a completely new way to ask the question. So how many other walls are we leaning against just because somebody once told us they were unbreakable?